Hello again, my name's Victor, and we are discovering the DFT together. Last episodes we talked about signals, discrete signals to be precise, and also about frequencies. And we left off at the question, what happens when we add signals together? I will answer this question this episode, and also answer the question of what happens when we multiply different signals together. In the 0th episode, I announced a little program which you can get in the description down below to play along while you watch this video. According to Fourier, we can reconstruct any signal if we have enough sine waves of different frequencies, phases, and amplitudes. Let's take a look in our software right here. In the top section, we have two generators. When we turn them off, we can see there's a green one and there's also a red one. In the section below, we can see the result when we add those two generators together. All generators have three knobs: a frequency knob, a phase knob, and an amplitude knob. Also, mind you, there's two little shortcuts that you can use. First of all, you can press Ctrl to snap to particular values, and you can use Alt to make fine adjustments. Go ahead, play. Once you've played with the frequency, phase, and amplitude knobs, and you think you know what they do, we will look at them together to discern what they're doing exactly. So let's turn off the output for now and the red generator. Let's only look at the green generator. Okay, so first of all, the frequency. When we turn the frequency, you will see, of course, there's more periods inside this frame. Yeah, that's what we learned, what frequency is. Frequency is how often the period appears within the window. Okay, let's turn it around, and let's turn it, for example, to 3. The value appears when I press the knob. When we turn it to 3, we will see that 1, 2, 3 periods are within the window. So this frequency gives us the value of how many periods happen within this window. When we turn the phase, you will see the sine wave shifts apart by one whole period, right? The phase is basically the position of the sine wave. We can also play around with the amplitude. Right now it's at an amplitude of 1, so this signal goes from 1 to -1, right? We can play around, and when we decrease the amplitude, of course, the deflection of the signal also decreases. When we turn it down to exactly 0, we get a perfect line at the axis, which means the signal is entirely 0 for the entire window. Let's push the amplitude further. When we push it further into the negative realm, the amplitude increases again, but in the opposite direction. Basically, what we are doing right here is we are mirroring the signal at the axis. This is what's called inverting the polarity of a signal. So now let's look at what happens if we have two generators and how they combine together. Let's turn on the output to see how they add up. And let's first try out the following. We set both of these frequencies to exactly 3 and the phases to the same value. And now you will see they perfectly align. They are totally in phase. Right here we have the red generator being 1 and the green generator being 1. And 1 plus 1 of course gives us 2. At this point both are 0, so 0 plus 0 gives us 0. At this point both are -1, so -1 plus -1 gives us -2. And that's what we see exactly in the output. The output signal is much louder, or has a much bigger amplitude than our input generators. This is what's called a constructive interference. When two frequencies align perfectly and are in the same phase, so they are in phase, and they have the same polarity, so they are not inverted like this, we call it a constructive interference. Actually, when they are inverted like this, they perfectly cancel out. And as you see below, in the output section, we have a perfect line because they totally cancel out. This happens because right here we have for the red generator a value of 1, and down below here for the green operator we have a value of -1. So 1 plus -1 gives us 1 minus 1 is 0. So we have 0 at this point. And the same happens right here. 1 plus -1 gives us 0. At any point, for each value of the green generator, there is a corresponding negative value of the red generator. And when they add up, we get a line that is perfectly at 0. Let's play around with the phase. Let's shift the phase further to maybe exactly half of the period. The two signals are as if they were inverted in polarity, but actually they are shifted apart exactly half the period. And thus we get a total line of 0 again. Now let's consider that we fix one of the oscillators using control to fix at the values at exactly a quarter of the period, right? Okay, now they are like half aligned. Let's turn around the green amplitude now. When we turn it around, of course the green signal gets lower, but also the amplitude of the yellow signal shrinks. When we are perfectly at 0, we have perfectly recreated the red signal, and then we can shift it further, and the amplitude rises again. That's clear, of course. But there's another thing that happens. Look at the phase of the output signal. When we decrease the amplitude, the phase shifts also, right? And if we increase it in the negative values, the phase keeps on shifting. Now let's do the same with the red generator. Let's now decrease the amplitude of the red generator. Of course, the amplitude of the output signal decreases again, but also the phase shifts further as well. Let's put it down into the negative values, and you will see the phase has shifted again, right? And the amplitude is back to this half-aligned kind of maximum. Okay, now let's push the amplitude of the green generator again. When we do this, we see the phase shifts even further. So if we do this all the time, change around the amplitudes of the different generators, we can continuously shift the phase. That's pretty important to note. We can combine a sine wave with another sine wave, which is a quarter of the period's offset, and play around with the amplitudes, and we can get a sine of any phase as a result. Let's test for another thing. Let's test what happens when we turn up the frequency maybe to say 11, and turn up the frequency of the other one to 11 as well. We will see, of course, a sine wave again. Let's put them in phase again, so we have a constructive interference. Okay, looks normal. But now, what happens when we put one of the generators maybe to a frequency that is 1 higher than the frequency of the green generator? We will now see this weird swelling down and swelling up again. Why does this happen? Well, let's look at what happens in the input section. First of all, both signals are perfectly in phase. They start perfectly in phase, and right here they have a constructive interference, right? And then the red signal is much faster, quote unquote, than the green signal. So they slightly offset themselves when right here they are perfectly out of phase, so that we have a destructive interference right here. And then the red signal is even as fast as to catch up to the green to the green signal again, so that we have a constructive interference at the end again. This is what's called a beat frequency, this swelling up and down, because this happens actually more often if we shift the frequencies apart more. Like for example, right here we have a frequency of 10 for the green generator and a frequency of 12 for the red generator. And right here we have the swelling up and down twice. Well, the frequency of this kind of swelling up and down, the beat frequency, can be calculated by calculating the difference between the two sines that we add together. In this case, we have a frequency of 10 and a frequency of 12. So the difference between those two is 2. And we see this swelling up and down twice per this frame. Makes sense. Okay, let's test it with a higher frequency, like maybe 16 and 14. As well, we see this swelling up and down happens twice per frame. Beat frequencies are actually pretty important. They will appear twice more when talking about different other phenomena. Can we use this addition or subtraction of signals to find the amplitude of several frequencies in a particular signal that we want to analyze? Well, unfortunately, we can't really. But there's a different thing that we can discover, which is what happens when we multiply two frequencies together. So now let's look at multiplication. When we multiply the two signals together, wow, what do we get here? Well, this is pretty interesting. But let's first of all look at a case when both frequencies are the same, like maybe 1. In this case, both frequencies are perfectly aligned right here and are the same frequency, exactly 1. What we see right here in the output is quite curious though. We see a sine of double the frequency, and it's also offset in the positive area, right? Why does that happen? Well, let's look at it step by step. First of all, when both generators are 0, right here, green and red are 0, so 0 times 0 of course gives us 0. Right here, both are 1, so 1 times 1 gives us 1. Right here again, both are 0, so 0 times 0 gives us 0. And right here we have minus 1 times minus 1, and that gives us 1 again. Let's shift the red generator apart a little bit, and you will see that at any point, any of the generators is 0. 0 times anything gives us 0. So at any point, right here, red is 0, so we have a 0 here. Here, green is 0, so we have a 0 here. Here's a 0, and there, and there. Makes sense, okay. But also what happens is we always have a sine wave of double the frequency. And it oscillates up and down, however we turn the phase now, right? Okay, so when we turn it perfectly out of phase, so the green generator is perfectly out of phase with the red generator, we will see that this output result is perfectly shifted downwards in the negative realm. Why is that? Well, we could look at it again step by step. 1 times minus 1 right here gives us minus 1, because minus times plus gives us minus. And right here, 1 times minus 1 also gives us minus 1. So this is totally shifted in the negative realm. That's pretty cool. Okay, that's a cool phenomenon. Let's shift it. Let's shift both generators up in frequency and see whether that happens in higher frequencies as well. Let's put maybe the 9th frequency. We have a frequency of 9 for both generators, and right there we see the same phenomenon. Makes sense, right? Okay. But what happens if we shift the frequencies apart slightly? Maybe 10. A frequency of 10 for the green generator and a frequency of 9 for the red generator. Suddenly we get this type of thing. Looks a little bit funky, right? Why do we have this lower frequency when we only had 2 high frequencies as inputs? Well, that is the case because when we look at it right here, both frequencies again are in phase, so we get a positive offset. When they are right here, they are perfectly out of phase, so we get an offset in the negative reaction, in the negative direction. And right here, they are in phase again, so we get a positive offset again. So for example, one generator is at 18 and the other one is at 16. 18 minus 16 gives us 2, and thus we have the beat frequencies with 2 periods per frame. These beat frequencies happen always when we multiply two signals that are of different frequency. And also important to note, the average of this entire frame of the entire graph right here is about at 0. And this is a very important note right there, because as we saw, when the frequencies perfectly align, we get an offset. And when the frequencies do not align, we get an average of about 0. So this might simply be our solution. If we multiply a test signal that we want to analyze with our test frequency, like a sine of a particular frequency, we can calculate the average of the output, and if the average is not equal to 0, we know that this frequency has to be in our signal that we are analyzing. But what happens if we shift the phases apart? If we shift the phases apart by exactly 1/4 of a period, you will see the output signal is again perfectly centralized around 0. But we could multiply our signal that has to be analyzed with 2 test frequencies. One of them is not offset at all, and the other one is offset by 1/4 of the period. And either one of them will give us an offset in average when the frequency is in the signal. So we can find out whether the frequency is in the signal or not by simply having 2 test frequencies. Let's have, for example, a complex waveform like the saw wave. When we put the frequencies down again, like maybe 8, we would take a test frequency and sweep it up the spectrum. And if the average is offset, we know that this frequency has to be in the signal. So let's do it. We sweep it up. Let's press Alt for this, so that we can very finely adjust it. And I don't really see any significant offset right now. Let's turn it further and find out whether we get some. And suddenly you see this happens, right? Wow, exactly at this point, at a frequency of 8, we have a offset in the negative direction. So we know that this test frequency is in the signal. When we push it further, let's press Alt again. It centralizes around 0 again, but when we push it and push it and push it, at some point this will happen. Okay, this looks like this is not centralized at the 0 line anymore. It's significantly in the negative realm, right? If you know anything about saw waves basically consist of the harmonic series. The harmonic series is every frequency that is a natural multiple of the fundamental frequency. In this case, our fundamental frequency is 8. The frequency of our test frequency is 16, and we get an offset. Makes sense, because 16 is a natural multiple of 8. Okay, let's push the generator further. And when we get close to 24, we get this again. And this looks like an offset. I think it's rather in the negative section than in the positive. It looks pretty regular. So this frequency is also in the saw wave. So we basically have all we need. We simply have to sweep our test frequency through the whole spectrum and then put all the pieces together. That's exactly what we will do, but in the next episode. Biggest cliffhanger! Can you even wait the discrete Fourier transform in the next episode? I cannot. Okay, anyway, bye.